Good afternoon. I hope the lunch was good. This is not siesta time, despite what you may have heard. So as Hadrian indicated, I'm going to be talking, and Mike and I are actually going to be talking about the local cyber infrastructure that is provided by ITS. So quick review here. The ITS mission, I'm not going to read the slides. I have a lot to go through. But you notice the very first one is to provide solutions in part that support research. So that's the aspect we're focused on today. Within ITS, we have a research computing group. Its mission is to facilitate cost-effective access to IT resources for the research community in many areas, and also to engage with faculty on emerging technologies that we might incorporate into our service offerings. All of what we do in this area is done in collaboration with the faculty advisory group. This has been extremely important and extremely helpful. We set this up at the very beginning. Faculty from throughout the university, we have interlocking membership with 2 faculty senate committees also. That committee approves the policies that are established for our HPC cluster, for our storage, for really all of our services. And very importantly, the faculty members of that committee over the years have been very strong advocates for us in getting funding from the provost and ongoing funding within ITS. So one of the most important and most popular resources we provide is high-performance computing. Actually support for high-performance computing. We have local HPC resources, which I'll talk about in a little bit more detail in a minute. We also encourage people actually to go beyond what we can provide. We like to have faculty outgrow what we can provide and help them get set up either at the state level with the state-funded Ohio Supercomputing Center or national resources through XSEED, funded through the National Science Foundation. I should mention that NSF XSEED has what they call a Campus Champions program, so we have local support. Hadrian is very active in that program. I'm on the books, but not very active in the last few years, but we're here to also provide support in terms of getting access to XSEED. Our HPC cluster looks like this. I won't read the slide. Notice that we do have GPU nodes. Dr. Will Bush mentioned the use of those in his talk. And I'll mention we are talking internally very strongly about adding to those with some newer GPUs, the K40 or possibly the K80 from NVIDIA. We have parallel storage inside of the cluster to support running jobs, interconnect based on Ethernet. And we have an experimental Hadoop cluster, so Dr. Jang mentioned the use of that. That was the cluster he talked about in his talk this morning that he had leveraged to get some nice results. Just some quick statistics. We, roughly speaking, over the last few years, we do about 10 million CPU hours per year, about 2 million jobs per year, and we've identified about $250 million of active funding, federal funding at CASE that's tied to our high-performance compute cluster. So these slides are a little bit out of date, but basically you can see the number of users by fiscal year has gone steadily up. The red line is faculty sponsors. Number of jobs by fiscal year has also gone up a lot. Number of CPU hours by fiscal year also up. And our usage is split pretty evenly among arts and sciences, medicine, and the School of Engineering. So getting access to the cluster is pretty easy. We provide free guest access. That's intended for short-term evaluation purposes, casual use, testing, and so forth. We'd like people to transition from guest use over to becoming members or investors in the cluster. So that's very important for us to keep it going. It's been very important over the years to be able to demonstrate to ITS leadership and to the provost's office that faculty think highly enough of this to build funding for this, some support for this into their grants. So we offer, again, hardware investment that's very attractive for people holding NSF funds, which are You really don't want to pay that 50% plus indirect on something other than a hardware investment. So we provide that, both options for that. Members get longer run times, higher priority, more simultaneous processors, more disk storage. We are working in the, as I mentioned earlier, on the big data side. So we have the experimental Hadoop cluster that GQ had mentioned that he used. We're also rolling out a pilot Hadoop cluster that's really more targeted for this kind of utilization. So the data nodes in particular have a lot more storage in them than we put in the original pilot Hadoop cluster, the experimental one. And the idea here is that we will expand this. This is being designed to be expandable as need hopefully increases. One thing that's become very important in the last couple of years is to provide for data storage. We've helped recruit a few faculty members here from other universities. Jonathan Haynes' name was mentioned, Phoebe Stewart in pharmacology, a few others, and they tend now to bring tens of terabytes of data with them. So we need to have a way to park the data here and also a way to move it. So that impacts our local cyber infrastructure. So we have our initial investment in storage was designed to be redundant, scalable, replicated between our two data centers, and we offer people the opportunity to use this either through a payment. It's based on what we spend on this. We don't increase it at all, or by buying storage to plug into the unit. And we have 4 different types of storage at this point that's suitable for research. The parallel storage inside the cluster, the replicated storage I just mentioned, the nearline storage that's based on a Dell product called Compellent, that's just about ready to go live. We're in final testing right now. And we are going to be building out some archival storage that'll be hybrid disk and tape, about a petabyte, and that should be coming later in 2015. The research network, very important part of what everybody needs here. So we got a CCNIE award. Dr. Ramnath mentioned the current CCDNI, that the CCNIE was the first of those 3 different alphabet soups of awards from NSF. So based on that, 2 years ago, we built out our connection to ORNet to 100 gigabits. We've done a lot of upgrades on campus to many campus buildings. Mike will talk a little about that. We created something called a Science DMZ that Mike will talk about. Software is another part of infrastructure here. So we have a whole list, I'm not going to read these, a whole list of titles available on the HPC cluster, as well as lots of titles available on the ITS Software Center, and I listed a few that are probably of interest to people doing research. In the area of visualization, we have software on the cluster to support visualization, ParaView and Visit being among them. We put up a visualization wall in the Kelvin Smith Library a few years ago. That's gotten some use. In particular, there was a group of NASA people there, I think 1 year ago, if I recall right, using the wall to look at photographic images of the planet Mercury, and they were really wowed with the ability to walk right up to it, get very high resolution look, and then just walk back a few steps and get the panorama all at the same time without zooming in or anything. We're working currently on projects with faculty in visualization in both digital humanities and biology. We do database design, programming, and hosting. This is something you may not have heard about. This is primarily in the medical school, but not only in the medical school, to support clinical trials, various kinds of studies. We don't force people to use this Apex system, but it's there. It works very well. It provides a web interface, and all the data is stored inside our data center. So there's a lot of security backup and so forth tied into that. One thing that's gotten very important to us, especially in the past few years, is to increase our work with faculty. And that includes working in a pre-award state, helping faculty to create their budgets, something as simple as writing a letter of support, agreeing to host equipment and services inside our data center for them as part of the project if they would get the award. We've collaborated, I think, this year so far on 14 different proposals that have gone in, and this fiscal year, I should say, so we've got a few more months to go. Some of those are led out of ITS. We did a submission just within the past week for the CCDNI program that Dr. Ramnath mentioned. We also had an MRI, Major Research Instrumentation, proposal go in January, and we're planning an NIH shared instrumentation grant to go in May with Jonathan Haynes, actually, in the med school. We're also looking to continue our engagement post-award. So we do have staff who are written into proposals, and then we participate in the project if the award is granted. So that's what I had to say. I'm going to ask Mike to come over now, and he's going to talk to you about the Science DMZ and something called our secure research environment.
So, thank you, Roger. I never can do these clickers very well, so I apologize if I go left when I'm supposed to go right. See if I do this right. Okay, great. So, I want to talk about two different things, the Science DMZ, which Roger's kind of already spoken about, as well as the secure research environment. We've mentioned Science DMZ a couple times today, and we kind of want to do a little bit more of a deep dive. So what are the 4 key concepts of a Science DMZ? It's a network architecture explicitly designed for high-performance applications dedicated to scientific research and development, rather than our traditional, crew network where, we have desktops, we have applications, we have servers and everything else that are doing more transactional email messaging kind of stuff. We make use of dedicated systems for data transfer to support scientific research with or without firewalls, essentially. We make use of host-based firewalls and routing, as well as ACLs within the routers to protect those systems. We also have the capability to do performance measurements to make sure that, not only are we able to send data very quickly, but we're able to measure it and do optimizations during that packet data flow. And then I mentioned this before, security policies and enforcement mechanisms that are tailored to high-performance networking and high-performance applications. So this is what our case Science DMZ looks like. This is partly from the NSF CCNIE grant that we were awarded 2 years ago. As Sue Workman mentioned earlier this morning, we were one of the first institutes in Ohio to go to 100 gigabit through Internet 2. So we now have a 100 gigabit Internet 2 connection, as well as ORANET connection, and soon to be one community 100 gigabit health tech corridor connection. That's all going into our router right here. And then we're able to take that over into our high performance computing network through a layer 2, which is basically the physical network and the cables and everything else. This allows us opportunity to do many different things now. For example, now we're able to marry what we're doing inside the high performance computing and the network into our Panasas storage that Roger mentioned, which is high performant. The other 2 pieces that are in here that I mentioned before is a data transfer node, which I'll speak to in a second ago, and then a perf sonar node. But all this stuff is segmented away from our traditional enterprise network where you see firewalls and the 129.22 IP addresses that we normally see in the schools and colleges, different buildings. So data transfer nodes. Basically, they're computer systems used for wide area data transforms, and they perform a lot better because they're purpose-built. There's not different services that are running on there, such as Apache or any other things. And they also are tied to only a couple of file transfer mechanisms, namely SFTP and Globus. Globus is a application that was hosted out of the University of Chicago and Argonne Laboratories, which came out of the Grid FTP system that was developed for, what is it? Not Future Grid. Do you remember what it is, Roger? TerraGrid. It was developed during the TerraGrid time. So it's designed for high performance transfer from and to remote systems. It can be provided here on campus as a stage area for large data sets that can be moved into the HPC because all of the same shares are mounted between the HPC and the data transfer nodes, or for local departmental servers. The key here is that when you do data transfers, it makes a lot more sense to stage it on campus and then transfer it locally, because when you stage it, it's going through our science DMZ, and then from that point, we can then look at the metrics to make sure that what's going on to the campus enterprise network has a fast path, essentially. So this is an example of us doing this over the summer. Dr. Lamframboise is in genetics and within the School of Medicine, and he makes use of what's known as the Cancer Genome Atlas, which is a data set hosted from UC Santa Cruz. Prior to us implementing the Science DMZ, he could get at best about a gigabit worth of data transfer. It basically utilizes a protocol called BitTorrent, but it's been modified so that it provides a little bit more security, but it still uses that same seeding, as well as being able to chunk the data and then make use of all these different distributed nodes that are on the internet to be able to quickly pull the data to our environment. Basically, by implementing the Science DMZ, we're able to get 3 times the speed and performance out of this. So now we normally see pulling from our data transfer node about 3 gigabits, where prior to that it was only 1 gigabit. So by going to this method of staging your data and then transferring it to your local machines, you get a lot more performance. And we're glad to help you guys if anyone wants to reach out to us to kind of do something similar to this for your labs. So as Roger mentioned before, we have been doing a lot of network upgrades over the last year or so, partly out of that CCNIE award. The CCNIE award funded upgrades in Glennon, Olin, White, Rockefeller, Wood, and West Wing. And this brought everything to 10 gigabit at the enterprise core as well as distribution layer. So we can now actually go to a faceplate and be able to connect it to 10 gigabits if the research and the lab requires that. ITS is funding similar efforts within the BRB, the Wood Research Building, Woolstein Research Building in Q4, and then Robbins East Wing in Q4 as well. So this is ongoing, and we are pretty much going to be doing this on a yearly basis, but these are the ones that we're targeting for this year. So as I transition, one of the other strategic initiatives that we started this year was the secure research environment. The secure research environment is a physically and network separate virtual environment designed to address a lot of the compliance requirements of our affiliated hospitals. So UH, the clinic, as well as Metro Health. A lot of these different affiliate hospitals have to work within the confines of HIPAA, and one of the things within HIPAA is that you have an adequate security plan that addresses the privacy and safety of patients. Because we work with these people, we have to follow the rules, essentially. So what we had to do within this environment is, up the game when it comes to information security. So this allows us, and I'll skip through this a little bit, to address the requirements for research within clinical data. We also have a lot of new regulations within the grants and contract side, in particular for FISMA. FISMA is the Federal Information Standards Management Act, and it's an act that basically makes all federal agencies as well as their contractors liable for any security breaches, essentially. So the way that we're protecting this environment will allow us to, one, handle HIPAA, but also allows us to future-proof ourselves when it comes to FISMA. And it gives us an overall benefit of addressing the increased concern regarding risk, as well as research data and bring your own devices into the workplace. So how are we doing this? Our approach is, as I said before, we're mainly targeting medical research, so HIP is going to be our main regulatory driver. But we're also using a lot of the best practices from FSMA, in particular NIST, which is the National Institutes of Standards and Technology. They have this special publication called 800, which kind of gives us a framework as well as different controls of how we're supposed to secure this environment. There's also another industry consortium called SANS that provides us, these are the targeted controls out of that NIST publication that you really need to have in order to secure your environment. So that's basically setting our priority of how we're securing this environment. And because we're kind of utilizing all those three things, we're able to scale us out to FSMA moderate as it's required. Over the last year or two, we've actually piloted it with many groups, including Center for Clinical Investigation, as well as Jonathan Haynes' Institute for Computational Biology and the Cancer Center. It's been quite successful, but really the key of this is that it provides us a way to give investigators a virtual desktop so that they have what they're comfortable with in regards to their Alphys applications, as well as SAS or Stata or any of the statistical applications that they're used to. And at the same time, giving them the ability to have network drive shares. So it's virtually the same as what you would have, within your campus lab or office environment. But it allows us to make use of information security practices and everything else that we currently don't have here on campus today. So this is sort of what it looks like. I mentioned before virtual desktops, but the idea, even with FSMA, is that great, okay, there we go. The idea is that you segment off an area within your network and environment and give it kind of a platform and boundary, basically. So the boundary is basically done through having this at a co-located facility, as well as having all of the firewalls, networking gear, servers and everything else residing in that controlled environment. Basically, we're going to be able to offer the secure virtual desktops that I mentioned before to researchers. They're going to be able to log into this using the Duo two-factor authentication that everyone knows about now here that we're deploying on campus, and then be able to access any web application or database or data set that you're accustomed to using today on your PCs. We're also allowing our healthcare institution partners the ability to log in via a web portal, because a lot of the different transactional database application systems that people make use of, they need to be able to have access, because that's the primary way that a lot of our research labs acquire data. So this is kind of the framework that we are making use of. Today, we're actually doing a lot of development for the Cancer Center through this environment design. So some of the successes that we've had over the last year or two is distributed research groups are moving towards using a lot of our central resources, which is a good thing. We definitely encourage us to collaborate with you in order to figure out ways that we can improve our services so that we offer you value and help you with doing grant proposals as well as your post-award activity. We also have been successful in kind of abandoning the concept that departments need to have their own HPC systems, that the central high-performance computing system that we have is robust and enables you to not have to worry about doing more of the administration of your own hardware. And the value add is that you focus on the software stack that you need for your research projects. We've also been able to recover some of the distributed data center spaces across the campus within all the different schools and colleges because of the collaborations we've had with different departments and labs. We do now provide research, data storage, and secure repositories through such activities such as secure research environment, as well as the research storage and archival capabilities that we're bringing online today. And then finally, the ability to make use of this as a recruitment tool for new faculty, which are all positive things. Any questions?
What's that map?
So this map is very interesting. Roger, do you want to explain it more, or because Dennis is actually the architect here of it, and he's sitting right there. So I can start this, but you guys are probably going to finish this. Mark Griswold, who is part of the Case Center for Imaging Resources, he does a lot of different MRI research, and part of this, IT's involvement was the fact that we have many GPUs in our environment that sit right here within the Kelvin Smith library. He also purchased GPUs. But in order to make use of this, he needed to make sure that his instruments, which are right here, were able to have a 10 gigabit link between the GPUs and the equipment that was sitting in his lab. So Dennis worked on this project in particular to find a physical fiber path that was very redundant, because what Mark was doing inside of his MRIs is actually working with non-magnetic instruments to basically, it wasn't surgery, was it? Okay, it was surgery. And basically being able to do real-time rendering of those MRIs, where prior to this, how long did it take to do the imaging? I don't know, it was
minutes anyway. It was not relevant to being able to do.
right. But this enabled him to do real-time imaging, where prior to that, it was take a snapshot, look at it, then do, some sort of surgical, incision or modification or something like that. I apologize, I'm not very fluent in this, but this was one of the things that we were able to do with the fiber plant that sits on this campus that, our CIOs a couple, instances back thought of doing. It's really creating, the vision of what we're going to be doing, years ahead. Thanks.